Hey, calculates. I bet you've missed me. It's been several days without me torturing you at home. So today we're going to look at implicit differentiation. And there's a difference between explicit form and implicit form of an equation. Explicit means I can write it in y equals. Implicit means when I look at that thing, that's a hot mess. I don't think I can get y by itself. But I'd like to be able to take the derivative regardless of which form it's in. So of course the first one, very easy for me to take the derivative of that because it is an explicit form. But the second one, not so much. Remember, two ways that we can write the derivative is we can either say y prime or dy dx. This is going to be important to us. This means we're taking the derivative of y with respect to the variable x, which is the other variable in the equation. So both of those mean the same thing. So in order to differentiate implicitly, one thing I want to be able to do is make sure that I'm differentiating both sides of the, that's supposed to be a THE, of the equation, with respect to x. So after I've gone through and I've differentiated both sides with respect to x, I'm going to collect all the terms involving dy dx, you're going to see a bunch of those in a minute, on one side of the equation. In other words, I'm trying to get all the dy dx's by themselves on one side. It's just an algebra step. And then as the last step, once we have all those dy dx's on one side, we're going to factor out the dy dx, and then we'll finish solving for it by dividing by the coefficient on it. Again, it'll just be an algebra step, so it won't be very hard. Okay, so let's look at some examples. And keep in mind, we've been talking about this whole idea of differentiability. So you have to remember it's not differentiable at a point if there's a vertical tangent. That would be a place where I would have asymptotes for one. We'll see some others. And it's also not differentiable if it's not continuous. One little note that you should probably draw down and sort of ponder over in your head is this. If we drew a Venn diagram and we called this circle continuous, struggling on the spelling, and then inside of it we could put another circle called differentiable. It is a differentiable. That's how those two fit together. So the question is, if I'm differentiable, do I have to be continuous? And the answer is yes, because if I'm differentiable, I automatically live inside the continuous circle. But if I'm continuous, do I have to be differentiable? The answer is no, because I could live out here. And so some examples might be, if I were doing an absolute value graph, that's continuous, but not differentiable at that point. Or if I have, let's say, a graph that looks like this, and I have a cusp. Continuous there, but not differentiable there. So that's just a good way to remember it in your head. So when I'm differentiating, I have to pay attention to what variable I'm differentiating with respect to. Typically, I'm differentiating with respect to x. So when I look at the problem, I need to check to see if the variable in the problem, or variables in the problem, match what I'm differentiating with respect to. And if they do, then I don't have to worry about taking the derivative any way other than I've already done. So in this case, I would be powering down and decreasing the power by 1, and so I'd have 20x cubed, which you already know how to do.